you have one independent variable, and so forth and so on. Today, instead, what I would like to do is to introduce the case of two-dimensional problem. So basically, what I would like to do is to start to solve systems of ODE, systems of ordinary differential equations. Okay. So suppose, for example, that I'd like to that you want to analyze this kind of system x prime equal to p of x and y, and y prime equal to p of and y. Close the microphone. Okay, thank you very much. So P and Q are supposed to be well-behaving objects. Okay, functions that are well-behaving. What does it mean? This means that I'm taking P and Q to be functions which are continuous and which has partial derivative that are continuous at any order. In some domain that I will call capital D, which is a domain contained in the plane x, y. Here, prime here denotes a derivative, for example, with respect to another variable that would take to be the time. So the prime is the derivative with respect to time. Do you remember what's the name of an equation which does not contain one of the independent variables? So, for example, when I have some equation like x prime equal to f of x, do you remember what's the name of this kind of equation? Where this term here does not contain t. No answer? Okay, this is the case of autonomous equations, okay? So exactly in the same way, when you have a system where on the left-hand side you have some differential operator with respect to a variable, an independent variable, which we say in this case to be the time, and on the right-hand side you have some function of the variable x and y, but not t, then the system is said to be autonomous. So this is basically a function of the state variables x and y that you want to determine, but is not the function of the independent variable which is t. Okay. Under these assumptions, so under assumptions that p and q are C infinity or class C infinity, so continuous with partial differential with partial derivative continuous at any order, then under this assumption we can claim the theorem of existence and unicity of the solution of the initial value problem. What does it mean? It means that if I'm considering the problem of solving this system here with certain initial condition given by x d t naught equal to some x naught and y in t naught equal to y naught, where x naught and y naught belongs to the domain D, then the solution, there exists a unique solution that I can write as x t y t which is a solution for the problem, for this problem here, with this initial values for the function of x and y. And this is these are two functions which are well defined for a certain t between, well, which is chosen in some interval a, b, interval that contains t naught. So t naught belongs to this interval a, b. So basically, the idea of this theorem tells you is that you are starting with the idea that you want to solve this this system. How many solutions do you have for the system? Well, the theorem tells you that if p and q are regular functions, then there exists only one and only one solution, xt and yt, which satisfies this initial condition, x of t naught equal to x naught, and y of t naught equal to y naught. There are different ways that you can use to plot the solutions of the initial value problem. In particular, there are these two ways that are the ones that you usually find in textbooks and when you are solving problems or other sources, wherever it is. So there is a first way, which is to plot the function x and y as time series. So basically, imagine that you have some specific function for x of t and y of t. Here you have a plot in which I have on the x-axis I have t and the time, and on the y-axis, well, either I have x or I have y. And what I'm doing here is to plot the two function of y as a function of t and x as a function of t. Okay, so what I'm doing here in this type of plot, what I'm doing is to consider x and y as two separate objects, different, distinct objects. And what I'm plotting here is exactly the shape of x and y as a function, seen as functions of the independent parameter t. However, there is another way to plot the solution of this kind of system, solution of this initial value problem, which is in terms of a phase plane. So what in practice I'm doing is to treat instead x and y as two parts of the parametric equation of a curve. So basically what I'm doing is to eliminate the independent variable, in this case t, from the expression of x and y, in such a way what I obtain is just one curve. Think, for example, about the equation for a circle. Okay, when you have the equation of a circle, what's the equation of a circle? It's in terms of x and y would be x squared plus y squared equal to some c squared, some r squared, which is the radius of the circle. What you have done here is to eliminate the some variable t. Indeed, what you can do is to write this in an explicit way, writing x and y in terms of sine and cosine, and explicitly the independent variable t. You can eliminate these, and you can plot directly the two in just one point, as well just one curve. For example, in this case, suppose that I'm plotting y as function of x, and we find something like this. So usually, when you're doing this kind of job, you are playing where is the what is t naught? Where is the t naught? So the starting point of the curve. you are including some arrow. Why you're including the arrow? Basically, the arrow is telling you how does the curve evolve with time. So the arrow is telling you that as you are increasing t, the curve is going in this direction toward the center. This curve usually, these curves are called orbits. Orbit.
Sorry, Prof. I have a question. In the name of the first plot, time. Sorry.
It's just a description in terms of time series. Time.
Okay.
Series.
Okay. Thank you.
Okay. Yeah. Now, consider the following. Remember that we have said that given this kind of problem and given these properties for the function p and q, there is the one and only one solution of the initial value problem. Okay? Which basically means that there is only one and only one orbit, one and only one curve of this in the phase plane, so one and only one orbit, which is starting from this point t equal t naught. And this is going to be true for any tilde and also for any point that you are choosing in the phase plane. There will always be one and only one, at most one and only one orbit passing through that point, not the at most. So basically this means that there will be also points where eventually you do not have orbits passing there. And the fact that there is just one and only one orbit also means another thing, that orbits cannot intersect. So since you do not have the possibility to have more than one orbit passing through a point, again, this is due to the existence and unicity theorem. This means that I cannot have an orbit with like this. This is not possible because this would intersect in this point. And this means that in this point, I would be able to construct two solutions of this system, system of ODEs with initial data given by this point here. Since this is not possible, then this means that because there is just one and only one solution of this problem, then this means that orbits cannot intersect. You cannot have this orbit here. All right. Now, something which is trivial, but it's good to repeat in order to fix the ideas. Also, in this case, in the case of system of two or these two-dimensional ODE systems, it's still holding the idea that of equilibrium. So just the writing was written here because of it. Okay, so a solution of the equation, this equation here, with this initial data, such that x of t is equal to x naught and y of t is equal to y naught, this is called a equilibrium of the initial value problem. What's here? The board is not clear. In which sense? That too much light?
No, prof, molto più così.
No.
No.
What about like this?
It's better.
Better?
Yes.
Better, thank you.
Yes, sir.
Okay, that's right. That's understood. Great. Then we'll see. Yeah. So we said that if I'm finding a solution to the initial value problem, which is a constant solution of this kind, so where xt is equal to x naught and yt is equal to y naught, this will be an equilibrium of the initial value problem of my system described by this initial value problem. Can you imagine in the phase plane what's the corresponding image of an equilibrium in the phase plane? Guys, come on, a bit of courage. I mean, there are not so many things that you can answer.
Are two lines, one horizontal and one vertical? Or no?
No, but I appreciate the attempt. No, actually, it's just 1 point. So in the phase plane, you will have just 1 point, which is the point x naught, y naught. You remember that the phase plane is just a plane of x and y. So if I have x naught, y naught, this would be just 1 point, for example, here. Okay? This thing here, this point is what is called a critical point in the phase plane. Now, note that the critical points, so equilibrium, so solution, constant solution of the initial value problem there, are such that since these values x naught and y naught are constant, you can easily understand that x prime is the x in the t, but if x is equal to x naught, this would be just 0. Here I have p of what? X naught and y naught. Y prime is again, it's the derivative with respect to t of y, but y is just y naught. So this is again 0 equal to capital Q of x naught, y naught. So what does this tell you? This tells you that in order to find the critical points, that's exactly the same thing that we already met for the case of just one ODE. So in order to find the equilibrium, in order to find the critical points, what I have to do is to solve this system where P and Q are some function. Now this system could be some algebraic system, this could be some transcendental equations, wherever you want. For sure, here you don't have any derivative anymore. Okay? In order to find this x naught and y naught, what you have to do is just to solve this. And this will give you the equilibrium. That is, this will give you the critical points of the system, of this problem.
Sorry.
Yes.
But I didn't understand why x prime and y prime became 0.
All right. Because I'm trying to understand what's what happens to the initial value problem for in the case of a equilibrium, in the case of a critical point. And the equilibrium is defined as that solution of this problem, which is a constant solution, with x t equal to some constant value x naught, and yt equal to some constant value y naught. This means that on this solution, on this particular solution, x prime, remember x prime, what's x prime? Is the x in the t. Okay?
Okay.
In the particular case, in the specific case of my solution, x of t is just a constant value, is x naught. So its derivative of constant is gonna be zero.
Okay. Okay. Thank you.
Right?
Thank you.
But then, of course, you have to consider the functions p and q evaluated in x naught and y naught, because p and q must be evaluated on the specific solutions that you are considering. In my case, the solution is x naught, y naught, so I have here p of x naught and y naught. Note that as a particular application of the theorem of existence and unicity of the solution of the initial value problem given here, this guy here, so the critical point, is a solution exactly as it has a solution in another orbit that solve the same system. What did we say about orbits? Do you remember? We say that orbits, because of the existence of unicity, cannot intersect. What does this mean? This means that if I have two orbits which are solving this system, this cannot happen. So what about instead one orbit and one critical point? Can an orbit pass through the critical point? Answer.
Yes.
Yes.
Can pass through the critical point? Why?
Because it is just have one answer.
No, basically no, it cannot pass through the critical point. And I will tell you why. You have to think about the critical point as just another solution of this problem. So the only solution, there is only one solution with this initial data solution of this system. If the only solution is the critical point, this means that you cannot have any other curve passing through the critical point. It's exactly the same of two orbits that cannot intersect. So an orbit cannot pass through a critical point. You can think about the critical point as a kind of orbit which is like shrink just to that point. Okay, so just using the existence of unicity theorem, you can argue that an orbit cannot pass through a critical point. What can happen, and we will see later, what can happen is that an orbit is approaching a critical point for t that goes to plus or minus infinity. We will see in a second why plus or minus infinity.
Professor,
Yes.
I couldn't understand these points because I can't understand why it's not a possible.
Yes. So we say that when you have an initial value problem, remember the initial value problem is basically composed of two parts. The initial value problem is the system of differential equations, like this one, plus some initial condition, some data that your problem is giving you about the values of x and y in some point t0. So the initial value problems means, hey, you have this system here that must be solved, taking into account this thing here, this data here. Okay? Now, the existence and the unicity theorem tells you that there is only one solution, only one at post. There is one solution of this system with this initial data. Okay? Now, whatever is the solution, either just a point or a curve, so an orbit, whatever it is, it must be unique. So there is just that solution passing through that point. Now, if you have, this means that you cannot have two orbits crossing, because two orbits crossing means that they are both solving this this problem for the initial value data given on this point, and this would not be possible because of existence unicity, because of unicity of the solution. But the same happens if the solution is like this point. If I have a solution which is just one point, this is enough for saying that in this point I already have the solution. Okay? And this means that because of unicity, I cannot have any other solution of the system with this initial value data, which basically means that I cannot have any other curve which is a solution of this problem and is passing through this point. The unicity theorem forbids that.
Okay, thank you.
Now, just because we will need later, there is a particular case of orbits where you have closed orbits. So orbits are not supposed to be always like curves, which are open curve. They can be also closed. Basically, when you have an orbit like this one, this would correspond to some periodic solutions. This means that imagine that you are passing through this point at the time t equal 0, and then you are waiting 1 minute, so 60 at t equal to 60, the curve will pass again through the same point. Okay? And every n 60 seconds, the curve will pass again through this point. Okay? Questions? Is this something which is violating the unicity theorem?
No.
Why?
There is a solution for every instance.
So because basically the point here would correspond to different t. Let me reformulate your answer. Yes, your answer really is it's okay. So in different instances, in different times, for t equal 0 or for t equal 60, means that here I have different initial values. So this would correspond to different problems, and I would not. I would prevent the violation of the unicity theorem. So, solutions like this, closed curves like this one, are allowed. Yes. No. Let's see a simple example in order to see how things are working with some number. So imagine that I want to solve well, let I have some system which is given by x prime equal to y and y prime equal to minus x. Okay, I'm not giving. I don't want to see expressed the initial value problem. I'm not settling down the initial value problem. In this case, I'm just giving you the system of ODEs, the system of two first order ordinary differential equations. What I would like to understand is what I would like to find is the equilibrium, the critical point of this system. Okay, this is very easy. What's the equilibrium for this system? Somebody. Can you see the system? It's x prime equal to y and y prime equal to minus x.
It's the origin.
That's good. Yes. So the equilibrium is the origin. How do you find it?
You have to put the derivatives equal to 0, and so you find y equal to 0 and x equal to 0.
That's correct. So, as we have said, the equilibrium, remember, we said that the equilibrium is given from this p x naught y naught equal to 0 and q x naught y naught equal to 0. So, basically, in this case, my p is just y. So, the equilibrium that I will call x naught y naught will have from the first equation y naught equal to 0, and for the second equation x naught equal to 0. So the equilibrium will just be the origin of the phase plane. Okay, that's fine. What about the orbits then?
Sorry, teacher, it's not clear.
Oh, it's written orbits. I just wrote orbits. What about orbits? It's not clear in the sense it's small or because it's you can't see where. Okay, so what about the orbits? Do you have any idea of what can be the orbit?
It's difficult to see the symbol.
All right, let me try.
It is not in focus.
Yes, with this pen, it's blue pen. It's not better than the other.
All right, I will try with the blue. But the point is that the blue is not working very well. Okay, let's orbits. Let's try. Okay, give me 1 second. I will find another one of these. Just 50 seconds. Okay.
Thank you. See you.
Okay, guys, let's try with this one. Hope it's working. Okay. So what we want to find now are the orbits of this system here. So for the orbits, you have to massage a bit the equations. What you can do is well, there are a couple of tricks that you can use to find the orbits of this system. I will start with one of the two tricks. For example, I'm starting from the first equation, x prime equal to y, and then I'm differentiating both sides of the equation, left hand side and right hand side. So what I have here is x prime prime equal to y prime. So on the left hand side, I have just the second derivative with respect to t of x, right? X double prime. On the right hand side, I have y prime, but y prime is given from the second equation, which tells me that y prime is equal to minus x. This basically means that the orbit must also satisfy this equation, x double prime equal to x. What's the solution of this equation? Sorry, x double prime plus x equal to 0. What's the solution of this equation? The solution of this equation is some xt equal to c1, some constant c1 times the cosine of t plus another constant c2 times the sine of t. And this gives you also for free yt, the second the second function. Why? Because you already know that y prime is equal to, well, that y is equal to x prime. So what you have to do is just to derive xt, and this will give you y. So the derivative of cosine is minus sine, so I will have here minus c1 sine of t. The derivative of sine is cosine, so this is plus c2 cosine of t. Now, written in this way, this will give me just what we have called before the time series. So what I can do now is just to plot x of t and yt on a graph in which I have t on the x-axis and x and y eventually on the other one, right? I do not want to do this. What I want to do instead is to eliminate the parameter t from the equation. How can I do this? Well, what I can do is to square x and y. So I can calculate x squared is this thing squared, y squared is this other thing squared. And then what I can do is to sum up the two contributions. I can sum this and this. So what I will obtain is x squared plus y squared is equal, well, you can do the calculation by yourself to convince yourself that this thing here is c1 squared plus c2 squared. So these are the orbits of this system here. So what are these orbits? Yeah. What are these
Sorry,
orbits?
why you have done the sum?
There are just two identities. What I want to do is to find only one equation which describes the orbit. Okay? I can leave it like this. So without the square, I can leave it like that. And what I would have is some parametric equation for one curve. Or otherwise, what I can do is to express them in this way, which is this one. That's actually the same. If you're able to draw the orbit looking to the parametric component of the curve from here, then you are allowed to do that. But I think that in this way it's going to be easier. These are just two identities, so I can sum up the things, and I will end up with this, which is what is that? What's this thing?
An ellipse.
The equation of orbit.
Yeah, that's okay. But what is this orbit? What is this object?
It's an ellipse.
Huh?
A circular.
Is it? No, basically,
Circumference.
the orbits for this system are going to be like these ones. Is this better? Is this black pen better? Can you see this?
Yeah, definitely more.
Yeah.
Great. So the orbits of this system is going to be these ones. So there are circles. These are all the orbits. Plus, I will have these critical points, which is the origin of the phase plane here. Now let's see an example which is well, less trivial than this one. Can I cancel? Can I cancel?
Yes, yes, yes.
Okay. Okay. Now, the second example is a system. The first equation is x prime equal to 2x. The second equation is y prime equal to 3y. Again, this is an autonomous system because the prime is differentiation with respect to t, or whatever, t, z, call it as you like. And the system does not depend on this independent variable. So the system is again an autonomous system. There is something interesting about this system, which is the following. If you look carefully to the equations, you can see that these two equations are not coupled, right? So in the first equation, there is just x and x prime. And in the second equation, there is just y and y prime. You do not have a mix of x and y in these two equations. Okay? Now, the equilibrium is like before, right? So the equilibrium is given by 2x equal to 0, 3y equal to 0, which gives you 0, 0. So the critical point of the system, this linear system, is again just the origin of the phase plane. Now, since the two equations are not coupled, what we can think to do is to solve directly the equations. So what is the solution x of t of the first equation, of the first differential equation?
We should be C1 cosine 0 plus C2 sinus 0.
Hold on, yes. No. Actually, this is x prime, not x double prime. So a solution in terms of sine and cosine would be if you had x double prime. Like before, x double prime plus x equal to 0 has a solution in terms of sine and cosine. So this one, the solution of x prime equal to x, or equal to 2x, or in general equal to alpha x, is going to be in terms of exponentials. So this thing here is some constant a times the
Exponential C1.
So-
A exponential
of 2t. Okay, so in principle you can solve this also in terms of hyperbolic sine and cosine, but probably you didn't see in this way the solution of this equation. But this equation can be solved by this object. In fact, if I'm taking the derivative of x with respect to t, x prime, this would be 2a times e to t, which is equal to 2 times this object is x, so 2x. X prime equal to 2x, which is this equation here. So the solution to the first equation is this xt equal to some constant times the exponential of 2t. The solution to the second equation, well, it's very similar. It's going to be some y of t. It's another constant that I call b times the exponential. In this case, is 3t. So this is some general solution of this linear system of first order of Higgs. I will have, of course, A and B will be fixed if I'm also giving the initial data. I don't want to give the initial data because I want to explore the entire phase plane. So I want to explore all the possible orbits, all the possible curves that solve this system here. Now, Lorenzo, so basically you told me why you are squaring, why you are doing this. In principle, would you be able to tell me what are the orbits of this system looking at these equations?
A square.
No. All right. So basically, the idea.
A square exponential power of 4t plus b square exponential.
Hold on, yes. In this time, I will not square. Okay. This time, I do not want to square. So the idea is that I eliminate the independent variable. So what I want to do is to write down an equation, which is an equation just in x and y, because in this way, this would be easy to put on the phase plane, which is a plane with x and y's. Okay, so how do I can eliminate t? In order to eliminate t, what I can do is to take the logarithm, the log on the left and the log on the right. So if I take the first equation, this would give me log of x of t, and on the right I have log of a times e to t. From lezione. Okay? Now, same for the second equation. Log y t is equal to log b exponential 3t. Okay? Now, do you remember what is the log of the product? The log of the product A times B is equal to what?
ln
So-
a multiply
Log A plus log B.
Log A plus log B. That's correct. So what I do here, I will write from in the first case, this is log A plus log d of exponential 2t. But log exponential 2t is equal to 2t, right? And that's actually the same that I'm doing here downstairs. So here we have log b plus 3t. Okay? Now, what I want to do is to eliminate this t from the system. So what I'm doing is to write in the first equation t as a function of all the other stuff. So this is going to be 1/2 of log x minus log a. The second one is going to be t, the second equation, t equal to 1/3 of what? Log y minus log b. Okay? Now let me write log x minus log a using exactly the same property that you tell me.
Log A
Log x over a, right? And the other one is log y over b. But now what I have is t equal to this and t equal to that. So basically this means that this term here and this other term here must be the same, must be equal. Right? So let me write here. This is 1/3 log y over b equal to 1/2 log x over a. I can multiply times 2. So you have 2 here, 2 divided by 2 is 1. And then I can multiply left hand side and right hand side by 3, and they have these 3 that disappear, and they have this thing here. Okay? Now, what is this thing? This is 2 times log. How can I write this? This is log of y over b squared. And the right hand side is log x over a cubed. Now, what I can do is to exponentiate on the left and on the right. So basically, this log disappeared. So I'm taking the exponential of this and the exponential of right hand side. In such a way that the log disappeared. And what I have at the end is y over b squared equal to x over a cube. If you want to write in a nicer way, you can write y squared equal to b squared over a cube times x cubed. So y squared equal to some constant, which depends on the initial data, times x cubed. Okay? These curves here are giving you the orbits for this system here. Now, let's try to draw the orbits. Constant. You can use some mathematical software to draw this thing. Basically, okay, 0, 0, the critical point, the equilibrium is this point here. What are the other curves? The other curves are gonna look like these ones. Okay? Any branches, so any of these curves, this one, this one, this one, this one, any of these curves represent a specific solution of this equation for certain initial data. Okay? So, for any initial data, for any set of initial data, you will have a set of A and B. And for any set of A and B, you will have one of these branches. Note that when I speak about branches, the branch is just this one. Okay, does not include also the other one which is going down. The thing that's going down is another branch. You know why? Again, for the unicity theorem. Because the guy here in the middle is a critical point. And I cannot have an orbit which is passing through a critical point because of the unicity theorem. Right? So all these curves depart from the critical point, but they are only arriving the critical point for t that is going to minus infinity. So in this case, this critical point here, this 0, 0, is what is called a node. Well, in this case, this is an unstable critical point because solutions are departing from it. So they are reaching it at t that goes to minus infinity, and as time goes by, the curves, the orbits, are going in the other direction with respect to the critical point.
Sorry, how you decided the direction of the arrow?
The direction of the arrow, you can decide it by looking at these things here. So basically, these guys have the expression in terms of t. Remember, this was x equal to a exponential of qt and y equal to b exponential of 3t, correct?
Sorry,
Yes.
Professor.
I'm finished because this is an important
Okay, all right. There.
important point. Then I will come to your questions. So now, as we are seeing, these branches are approaching the critical points only when t is going to minus infinity. Correct? Why? Because the limit of x for t that goes to minus infinity is 0. And the limit of y for t that is going to minus infinity is 0 again. So this critical point is reached by, for example, this orbit only when t is going to minus infinity. So imagine the time starting from t equal to minus infinity, and then time goes in forward, just in one direction, forward. So you are increasing time. If I'm increasing time, means that I cannot go in this other direction because here there is the critical point. The only direction that I can go is in this direction. So when I'm increasing time on these branches, I'm going surely in this direction. I hope that's clear in this way.
Okay, so the first thing that I have to do is to find the critical point, and after do the limit with t, and so the arrow goes in opposite direction.
The arrow goes in the opposite direction just because, well, depends on how you are reaching the critical point.
Okay,
So
okay.
we can see later cases in which the orbit is reaching the critical point for t that goes to plus infinity. If the critical point is reached when t goes to plus infinity, this means that the arrow would go in the direction of the critical point, not on the other direction. Clear? Not?
Yes, yes, thank you.
This is something that must be clear. Yeah, what was the other question?
I got my answer.
Teacher, so
Hello?
Excuse me, I got my answer. I was trying to ask a question, but I get it. Thank you so much.
Great, perfect. Now, yeah, we have seen two kinds of critical points until now. One is the node. The other one that we are seeing is the center, which was basically a critical point surrounded by closed orbits, circular ones of before. Actually, for linear systems, there are other two kind of critical points. So this is a node. This is a center. And let me know here. So there are some critical points which are called saddles, S-A-D-D-L-E. So imagine that the saddle is in the origin, then orbits would do like this, and this. Let me comment, okay? These are going to be two lines. We will see in a moment an example of saddle, okay? In this case, I have one line with the arrows which are departing from the critical point. So one arrow is going up and the other arrow is going down. And then I have another line, which is this other one, with the arrows instead that are pointing toward the critical point. Say it again? No. Okay, so with the arrow which are going toward the critical point. So these two lines here are approaching the critical point, and these other two are instead departing from the critical point. And then I have these other orbits with the arrows, which are basically following the arrows of these two, of these two, of these two, and of these two. We will see an example of this because otherwise it's difficult to visualize it. There is another kind of critical point which is called spiral critical point. Which is basically a critical point which is approached this is an orbit, typical orbit, which is approaching the critical point. We approach it with the spiral. Okay, so these are all the possible kind of critical points that you can find for linear systems. Okay. Note that I'm specifying the fact that they are linear systems, because if you are considering systems that are not linear, what you will have, you can have some critical points that behave like a node in one side of the phase plane, and like, I don't know, a saddle in the other side of the phase plane. Okay, but for linear systems, critical points are always of these four kinds. Now, next, what I want to do is to try to understand if it's possible to say something about the stability of the solutions, the relation between stability of the solutions and critical points. Do you remember the issue of stability that we were describing last week when we were considering just one ODE with some initial value data? And we were saying that the equilibrium was stable if starting with data close to the equilibrium, we were still having a solution inside a certain interval, and the equilibrium was asymptotically stable if choosing data inside an interval close to close to the equilibrium, the solution corresponding to that initial data would approach the equilibrium in an infinite amount of time. Now, what we want to do is to search for some similar result also in the case of systems of two ordinary differential equations. So we want to start to define what's the relation between stability and critical points.
Teacher,
Yes.
we have to do some exercise for this different type of linear system.
I'm gonna give the exercise last week. I gave some exercises last week in order to
To practice.
Yeah, exactly. To practice a bit on this kind of problems. Tomorrow, I will do also some exercises to practice a bit on these problems. What I would suggest you to do is try to do it by yourself. These are simple problems. If you're not able to do these problems, please write me an email, send me an email. I cannot solve the problems also during the class because otherwise I would not have the time for doing anything. So what I would prefer is try to solve these exercises by yourself. If you cannot solve the exercise by yourself, ask me by mail and I will answer you. Okay?
Thank you, teacher.
That's great. Now, a critical point is said to be stable if for any epsilon is a small number that I can choose, there exists some interval delta epsilon such that every solution starting for some t0, so for some initial condition, for some initial data t0, the solution is starting into this interval delta epsilon, starting for some t0 inside delta epsilon. It remains inside delta epsilon for anything. So basically, what does this mean? Imagine that I have some critical point here. Okay. Now I give you some number epsilon larger than 0, greater than 0, and I say, okay, that's fine. Let me define a circle delta, which has the center here in this point, this critical point, and has radius epsilon. So basically, I'm defining this circle here. Now, what I'm saying is that this point here is stable if any solution which is starting from here inside, so for t0, the solution, for example, is here. If this solution continues to stay here inside this circle, then in this case, the point is said to be stable. The critical point is said to be stable. That's, for example, the case of a center. So you remember that the center was a critical point surrounded by closed orbits. Well, as you can easily see, I can define some epsilon greater than 0, such that I have this region here. And every solution which is starting from a point inside this region remains inside the region for any t. Okay? This is the condition for the critical point to be stable. In particular, the stable point would be locally asymptotically stable if for this thing, the solution is not even just staying in this region, but is approaching for t that goes to infinity to the critical point. So in this particular case, the critical point would be said to be locally asymptotically stable. We've said that the center is a stable point, but a center cannot be locally asymptotically stable because the orbits are closed orbits, and since they are closed orbits, they are not approaching the critical point. Okay. Instead, a node or a spiral can be eventually locally asymptotically stable, but they can also be unstable, because this depends on the fact that the orbits are approaching the critical point or departing from the critical point. And the saddle, instead, it's always unstable because there is always some of the orbits which are departing from the critical point. So what we want to understand, what we want to build up is some criteria that allows me to understand if a critical point is stable or unstable. Again, you can consider the analogy with the problem that we solved last week. Last week, speaking about the stability of equilibria for first order ODEs, you remember we were considering the fact that the derivative was larger than zero or was positive or negative, and this would allow me to say that a point, an equilibrium, is derivative less than zero, equilibrium is a stable equilibrium. Derivative greater than zero, the equilibrium is an unstable equilibrium. So what I want to do is to find some similar ideas for saying that the critical point is stable or unstable. And that's what we are going to do for the next minutes and probably also a bit tomorrow. So in order to do this, what we can do is try to linearize the problem and to study the linearized version of the problem. So what's the idea? The idea is that I have some system of ODEs that can be as much complicated as you want, not necessarily a linear system. I want to linearize the problem, so I want to reduce my problem to a problem of a linear system of ordinary differential equations. Then what I want to do is to study the criteria for the stability of critical points for linear systems, and then try to understand if it's possible to take these results and to use it for the case of non-linear systems. So in the case when P and Q are non-linear function of the state variables x and y. So the first thing that we have to do is to linearize, then to try to understand how we can linearize a system of ODEs, which is basically very similar to what we've done last week again. So imagine that I'm starting with some that I have a system which is but let me suppose that the system is exactly this one. X prime equal to P of x and y, and y prime is equal to Q of x and y. Suppose that this system has a critical point in x naught, y naught. So x naught, y naught is a critical point for the system. Now, what I'm going to do is to linearize, to expand around this critical point. So I will assume that I can write x of t and y of t as x naught plus u of t and y naught plus v of t, where u and v are small perturbations. So let me repeat. What am I doing here? Here I'm taking a critical point, x naught, y naught, and then I'm looking to solutions xt and yt of my problem, which are close to the critical point. So xt is close to x naught, and the y of t is close to y naught, because these u and v are small perturbations. Why am I doing this? Because, as I said before, what I want to do is try to understand if there is any criteria that ensure the stability of the point. Remember that stability implies some condition on paths, on solutions, which start close to the critical point. So this solution here is close to the critical point. What we will see, what we will look for, is the behavior of this solution that starts close to the critical point, and we will see if this is close enough to the critical points in order for the critical point to be stable or not. In any case, what we want to do now is to expand, linearize the nonlinear system around the solution of the critical point. So we decide these xt and yt. We wrote xt and yt this way. Now what I'm doing is to take this ansatz of solution and cook it inside this linear, this system, this nonlinear system. So here I have x prime. What's x prime? X prime is the derivative with respect to t of x naught, which is 0, plus the derivative with respect to t of u, which is u prime. U prime is equal to what? To p of x and y. What's x? X is x naught plus u, and y is y naught plus b. I can do the same for y. So y prime is equal to y0 prime, which is 0, plus b prime. So here I have just b prime. And it is equal to q of x, which is again x naught plus u, and y, which is y naught plus b. Now, what I'm doing here is to Taylor expand these functions around x naught and y naught. So what I have is p evaluated in x naught, y naught, plus the derivative of p with respect to x evaluated in x naught, y naught, and multiplied by u, plus the derivative of p with respect to y evaluated in x naught, y naught times v, plus higher order terms that I don't care. The same here, q evaluated in x naught, y naught, plus the derivative of q with respect to x evaluated in x naught, y naught times u, plus the partial derivative of q with respect to y evaluated in x naught, y naught times b, plus higher order terms that I don't care. Now, questions. This is something that you should remember. How much are these two quantities, P of x naught, y naught, and Q of x naught, y naught? What's the value of these two quantities? Somebody, please.
Is that 0 because it's a critical point?
Oh, yeah, that's correct. P of x naught, y naught are, and Q in x naught, y naught are not 0 because by hypothesis, x naught, y naught is a critical point. So this means that being a critical point, these two evaluated in x naught, y naught must be 0. So what I end up is that if I'm expanding these two equations, these two functions, sorry, around x naught and y naught, I will end up at first order with just these things. Okay, let me rewrite the system. System is u prime equal to, let me call, these are numbers, so these are coefficients. Let me call the derivative of p with respect to x evaluated in x naught, y naught, I call it A. The derivative of p with respect to y, x naught, y naught, I call it B. And I'm doing the same here, and I call this C, and I call this other thing D. So at the end of the day, what I have is u prime equal to AU plus BV, and B prime equal to CU plus B times B. Now, in particular, the matrix of these coefficients, so the matrix of A, B, C, and D, and the coefficients of this system, is what is called the Jacobian matrix. Why did we do this? Because we started with the nonlinear system. Remember, P and Q are generic functions of x and y. And what we said is that we can expand around the critical point x naught, y naught. And we ended up with the system that is linear. So we started with a nonlinear system, and we ended up with a system which is linear, whose coefficients, this Jacobian matrix, are coefficients that depends on the derivative of P and Q. So why did we do this? We did this because now what I can do is to study the stability directly only on the linear system. And what I will do later is to try to understand if the information that I get on the linear system can be translated on the nonlinear system. So next, what we will do, if any problem up to now? Any question? Now, what we will do then is to analyze the case of linear systems. Since there is no problem, let me cancel everything. Fantastic. Now then, let me consider. Let me cancel also this thing because now it's useless. Let me consider then the linear system of first order ordinary differential equations, which is given by x prime equal to ax plus by and y prime equal to cx plus by. Let me assume that AB minus BC is different from 0. Basically, probably you can already understand why I'm assuming that AB minus BC is different from 0. The idea is that this allows me to say that there is for sure a critical point in 0, 0. Why? Because the critical point is given by the system ax plus by equal to 0 and cx plus dy equal to 0. And I know that this system has solutions. Actually, there is a single solution. If the determinant of the matrix of the system is different from 0, which is actually the case by hypothesis, by assumption. Now, what I can do is to write this system here in some vector notation. So basically, what I'm doing is matrix notation, vector notation, matrix notation. So what I can do is let me define some vector x of t, which is basically given by x and y. So the vector x prime of t is some vector whose components are x prime and y prime. Then let me define some matrix A, which is basically the matrix of the coefficients of this linear system. So this A is A, B, C, and D. And then I have the vector x, which is a vector whose components, of course, are x and y. Can you see that this thing is equivalent to this system here? Huh? So basically, if I'm doing the matrix multiplication, right? So I'm multiplying first row by this column here, and I get ax plus by. And then I can multiply the second row by this column here, and I get cx plus by. So basically, this system here tells me x prime equal to ax plus b prime, and y prime equal to cx plus by, which is exactly these two equations that I wrote here in the system. So this shows me that I can write my linear system in this matrix form, in this matrix notation. Don't forget that by assumption, the determinant of the matrix A is different from 0. Now, what we want to do is to find some solutions of this equation here, written in this matrix form. And more or less, I can be guided by the fact that, remember, the solution of x prime equal to alpha x is something that goes like x equal to some constant kappa times the exponential of alpha t. So what I want to do is to give an ansatz, so to give a possible idea of solution of this equation, and then see what happens for the ansatz to be true. So the ansatz that I'm giving is that the solution x of t is written in terms of some constant vector v times the exponential of lambda t. I'm asking that the solution of this equation here is something that looks like this thing here. Where v and lambda, this is a vector, this is a number that I have to determine. So what I can do, I can take this thing here and put it here inside this equation. Let's see what happens. X prime of t. X prime of t means the derivative of this thing here. The derivative of this thing here is v times lambda times the exponential of lambda t. Lambda v exponential lambda t. And then I have the right hand side, which is the matrix A times the vector x, which is exactly v times a lambda t. Now, what you can do is to simplify the q exponential on the left hand side and right hand side. And you end up with this equation. So you have, let me write in this other way. So let me do this on the left side. Does this remind you of anything? What is this equation here? Guys, these are concepts of linear algebra, first year. So this is an eigenvalue problem. Right? So this equation is the equation that tells you that you are starting with some matrix A. When you are applying this matrix A to certain vectors, which are eigenvectors, what you will obtain is some number, lambda, the eigenvalue corresponding to that eigenvector times the eigenvector. What I want to do is to find these eigenvalues and these eigenvectors. Okay? Now, in 2 dimensions, because we are in 2 dimensions, so these V are vectors in 2 dimensions, this A is 2 by 2 matrices. In 2 dimensions, I can at most find 2 solutions, 2 eigenvalues, lambda 1 and lambda 2, to this eigenvalue problem. Now, as a matter of fact, what will happen is that depending on the sign of lambda 1 and lambda 2, and depending on the the relative magnitude of lambda 1 or lambda 2 in the sense of who is larger between lambda 1 and lambda 2, you will have different behaviors of the critical point. So let me repeat. Since we are in 2 dimensions, this implies that there are 2 at most. At most 2 distinct eigenvalues. That I call lambda 1 and lambda 2. And depending on the sign of lambda 1 and lambda 2, and who is larger between lambda 1 and lambda 2, I will have different behaviors of the critical points of the linear system. And the last thing that I want to show you today is what happens for lambda 1 and lambda 2, both positive, real, and distinct. So what I want to do is to analyze the case of the solution of the eigenvalue problem when both lambda 1 and lambda 2 are larger than 0 and they are different and real. So you remember our ansatz, the ansatz of our solution was some x equal to b times the exponential of lambda times t. This was the ansatz of the solution of the linear system that we were looking for. Okay. Now the fact that I have 2 distinct eigenvalues for the eigenvalue problem, probably you don't remember this, but again, try to have a look to your previous courses in linear algebra. So if you have 2 distinct eigenvalues, lambda 1 and lambda 2, to this will correspond 2 linearly independent eigenvectors b1 and b2. So this problem will have 2 solutions. One solution with the lambda 1 and some b1, and another solution with the lambda 2 and some b2. Where b1 and b2 are linearly independent vectors. Now, in this case, where they are linearly independent vectors, this means that the general solution of the differential equation, so x t, can be written as a linear combination of the linearly independent vectors, linearly independent solution of this vector. So this can be written as linear combination, so some constant c1 times v1 exponential lambda 1 t plus c2 v2 exponential lambda 2 t. Okay, this is going to be the general solution. This is a vector. Remember that this vector means basically that this is a 2-component vector. Here inside you have both x of t and y of t. Is it clear? If I'm putting, if I'm setting C1, let me set C2 equal to 0. If I set C2 equal to 0, it means that I don't have these terms here. So what I would have is just this term here, and this term here would correspond basically to some linear orbits in the phase plane. Linear orbits which are parallel to the vector B1. On the other hand, if C1 is equal to 0, I do not have this piece here, so I have just these other things. So what are the orbits? Again, we have some linear orbits which are parallel now to plus or minus B2. So basically, these are what are called the separatrices. In the phase plane, this would be basically these guys here. So one corresponds to, suppose that this is B1, so this 1 and 2 correspond to plus minus B1, and 1 and 2 correspond to plus minus B2. Any other orbit will be a combination of the two. That's a combination of the two. We can say also something more. We can also say something more about this combination of the two. We can say how an orbit is behaving when it's approaching the critical point. Because when the point is approaching the critical point, remember that my hypothesis lambda 1 is smaller than lambda 2. So if I'm approaching the critical point for t that goes to minus infinity, this means that this term is dominant with respect to this other one. So approaching the critical point, so for t that goes to minus infinity, the general orbit will be parallel to V1. On the other hand, for t that goes to infinity, this term here is subdominant with respect to this other one, so the general orbit will be parallel to the vector B2 for t that goes to infinity. And I think that for today it's enough. There is already a lot of material. Actually, just to this is in a stable law. This is the reason why a stable law. For today, it's enough. I don't know. Do you have any questions, problems, doubts, curiosities, or complaints?
Professor, could you please explain the last point? If you in the infinity, what happened for this paragraph?
Great. So.
Yeah. I'm sorry.
Let me start from one thing. Let me suppose that I'm taking the solution for C2 equal to 0. Okay? So the solution for C2 equal to 0 is just C1 V1 E lambda 1 T. Where lambda is a number which is greater than 0. Okay? When does this solution is approaching the critical point? Remember, the critical point is 0, 0 for this case. The critical point is approached when t is going to minus infinity. Okay? So, because for t that goes to minus infinity, this thing is 0. So this means that as t is increasing, this solution is going apart from the critical point. It's leaving the critical point. Now, this solution here corresponds to two branches. One is a plus V1 branch, and the other one is minus B1 branch. So basically, this solution here, without this part, corresponds to this and this, for example, with the arrow which are going in opposite directions and which are leaving the critical point. Again, because remember that the critical point, I cannot pass through the critical point. I remember that I can approach only the critical point for t that goes either to plus infinity or to minus infinity. In this case, I approach the critical point for t that goes to minus infinity, which means that going toward the future, I'm going away from the critical point. So going toward the future, the arrow tells me where is my future. Okay, so I'm going away from the critical point here, and I'm going away from the critical point here. The same happens for these other solutions. So let me set now C1 equal to 0. I don't have this, and I have just this thing here. Again, this guy here is equal to 0, goes to 0 when t goes to minus infinity. So for t that goes to plus infinity, for t that goes towards my future, I'm going away from the critical point. So the two branches, minus V2 and plus V2, which are going like this and this, for example, this is just an example. I don't know if this is like this one. So my future are going like in this way or in this other way. Right?
Yes, thank you.
Any other some combination of these two. How is going to be the combination? Well, this depends on the fact that lambda 1 and lambda 2 have some specific relation between them. So we say that a general orbit will start parallel to B1 and we then approach a kind of, it's going to be something like this. Because it's starting, which is parallel to B1, and then it's approaching to some solution, which is parallel to B2. So you will have some branches of this, and this is behaving exactly like a node that we show at the beginning of the lecture, or the middle of the lecture. It's an unstable node because all the branches are going apart, going away from the critical point. Any other questions? No. Great. Amazing. Then let's close here the lecture, and we will talk tomorrow. I don't know if it will be in Savona or again on Teams. We'll wait for information. I will send you an email as soon as I know what will happen tomorrow. Okay. Thank you very much, guys. Cheers.
Okay, thank you. See you tomorrow.
Okay, thank you. Bye.
But
Thank you, Professor. Bye.